How do you say it's like it's not solid, it's yeah, it's that's the term. I know, yeah, yeah, you're right. Jesus.
All right, there's a couple problems to work on before we get started.
Oh my God,
All right, you should definitely work on this problem because I would be not surprised at all if it was on your midterm on Monday or something like it. All right, let's talk about it. So, one of these should be a disk, one of these should be a washer, and has nothing to do with which axis you're going around. It has I mean, it does, but it's not like x-axis is for sure disk, y-axis is for sure washer, or vice versa. And so, hopefully, Dr. Dedell clarified the solutions to discussion sheet number 6, that there were some errors on the people talking about when to use washer, when to use disk. So we know we use the disk method if the region is flush with the axis of rotation. We're sitting on the axis of rotation, or the axis of rotation is one of the boundaries. So for these two problems, we should definitely be using the disk method for part B, because that region is touching the y-axis the whole time. On the other hand, for the x-axis, it's definitely going to be the washer method, because the region, there's some separation from the axis of rotation. Now, what you really should do here is whenever you're doing this, if you're going around the x-axis, or whichever axis, you should always draw a little vertical strip or a horizontal strip that is always perpendicular to your axis of rotation. No questions about it. So for the x-axis, I'm thinking I'm going to draw this little strip here somewhere in the middle of your region. I'm drawing it vertically, so it's perpendicular to the axis of rotation. And then I'm noting, oh, look, it's not touching my axis of rotation. I know it has to be the washer method. I know that this is going to be my inner radius. This is going to be my outer radius. So here, the volume should be, we'll worry about the limits of integration in a second. The volume is going to be pi times the integral from somewhere to somewhere of my outer radius, which is 11 squared, minus my inner radius, which is the function x squared plus 2 squared dx. I imagine you all could agree that my limits of integration are going to be as low as x equal to 0, because this thing certainly goes as far left as x equal to 0. But to find the upper limit of integration, we need to set the functions equal to each other to see where they cross. And if we set x squared plus 2 equal to 11, we get x squared equal to 9. We get x equal to plus or minus 3, but clearly it's positive 3. That point right there is the point 3, 11. So the upper limit is 3. For the second part of this question, going around the y-axis, well, now our axis of rotation is a vertical line, so our little strip better be perpendicular to it. It better be horizontal. So now this is our strip. And since our strip, no matter where we draw it, is sitting against the axis of rotation, it has to be the disk method. Or alternatively, you could say your inner radius is 0. And say it's the washer method, but the inner radius is 0. I don't love that so much, but it's fine. So here, using the disk method, the volume is going to be pi times the integral of just your outer radius. And our outer radius here is this function. Now be careful. You used a horizontal strip. The thickness was dy. We better be writing a function of y in here, not a function of x. So I can't write x squared plus 2. I have to solve for x as a function of y. So if y is equal to x squared plus 2, y minus 2 is equal to x squared. The square root of y minus 2 is equal to x. Now, I'm kind of leaving something out there. Technically, it's plus or minus the square root of y minus 2. But since we are on the right side of the coordinate system where x is positive, x better equal the positive square root of y minus 2. So it's the positive square root of y minus 2 squared. From as low as, oh, how low do we go? Well, it's not how low the x values are, it's how low the y values are. So if we look at this point right here, where x is equal to 0, well, y is going to be 0 squared plus 2. That point right there is 0, 2. So our lower limit's going to be y equal to 2. Our upper limit's going to be y equal to 11. Let's do two more with it. Let's continue this picture just for one more minute, a few more minutes, because I do think you might get asked something about like rotating around a different axis of rotation. So let's do that, and then we will move along. So let's say we were asked to, now go around the line. Sure. Y equal to 15. So now my region looks vaguely like this. X-axis, y-axis. And here's the line up here. Y equal to 15. My axis of rotation is horizontal, so my strip better be vertical. Does my strip touch my axis of rotation? Yes or no? No, definitely not. So if your strip doesn't touch your axis of rotation, we know it's the washer method. Ooh, that's not a good question. So my outer radius is that. My inner radius is that. Oh, sorry, you guys take place up. So the volume here is going to be pi times the integral from 0 to 3, because we're going as far left as 0, as far right as 3. But now my outer radius is the difference between the axis of rotation and the function we're looking at, which is y equal to x squared plus 2. So it's going to be 15 minus parentheses x squared plus 2 quantity squared. That in the brackets is your outer radius minus your inner radius squared, which is going to be 15 minus 11. Yes, you could write 4. So here's something I think would be a good question. I don't know if you get asked it, but I just think it's kind of neat. If I drew this picture for you, I could ask you, what are the only axes you could rotate around that would let you use the disk method? Well, we already used one of them. It was the y-axis. What's the other axis of rotation we could use that would still allow us to use just the disk method? X equals 3 is a good guess, but it is not correct. Here's why. But let's not. So before I get another answer, that was actually going to be my next choice anyway. So x equals 3. The reason why that's not going to allow us to use the disk method is because if we look at our axis of rotation here, and we draw a strip that is perpendicular to that axis, and you draw it anywhere in the region, it doesn't always touch the axis of rotation. What's another choice? Y equals 11. Y equals 11 is one of the boundaries. So it's a good candidate as long as it's a straight line for being an axis of rotation that's going to allow you to use the disk method. And it is. So here, if we did rotate around x equal to 3, so again, we're going to have to use a dy here. So here the volume would be pi times the integral from as low as y equals 2 to as high as y equals 11. Your outer radius squared minus your inner radius squared, dy from 2 to 11. Our outer radius is that distance there, which is going to be 3 minus 0. You don't have to write 3 minus 0, but I do think it helps people see that you really know what you're doing. And then my inner radius is going to be that right there. It's going to be 3 minus the square root function we came up with before. It's going to be 3 minus the square root of y minus 2 squared dy. There's your outer radius. There's your inner radius. And you should try to subtract the bigger thing minus the smaller thing. So in each of these examples, the bigger thing was the axis of rotation, so we did the axis minus the function. But if your axis had been down here, you would do the function minus the axis. Or if your axis had been over here, it would be your function minus the axis. Okay. I think I said enough about volume, but I just want to make sure because I did notice yesterday there were some errors in the solutions to homework discussion sheet number 6. And so I want to make sure it's really clear when and why you use the disk versus the washer method. It's all about, is the region rotating around an axis that it is flush with, that it is sitting on the whole time? Any questions about any of that? That's interesting. Okay. Let's go ahead and continue talking about some 7.2 stuff. Yeah. So I know last time we talked a bit about solving differential equations, but I feel like I kind of skipped some of this equilibrium and stability stuff. So we should go back to that. So section 7.2 is equilibrium and stability. And hopefully you've all seen like if you're into Dallas class, which I know is the majority, but not all of you, that he like emailed out contents of your next exam, and it's like up through section 7.4, I think. So 7.1, 7.2, and 7.4. 7.4 is the solving differential equations that are separable like we did in class on Wednesday. No mention of first order linear differential equations, so that's good. We'll hold off on that until it shows up. All right, so let's say we have the following. Suppose a population of squirrels is growing according to the differential equation dn dt is equal to 2 times n times 1 minus n over 1,000. Right, so we have the rate of growth is a multiple of the population size and this other thing here, which is kind of limiting how big the population can get. So the first question we're going to ask is, what are the equilibria? Meaning, what population size could the squirrels get to and just kind of maintain, where the population wouldn't be changing? Well, if we're asking this question, we're really asking what values of the population size, which is n, make it so that the derivative is equal to 0. Right? If we're talking about equilibria, we're talking about things not changing. If things aren't changing, the rate of change better be 0, meaning the derivative better be 0. So you take what your derivative is equal to, and you set that equal to 0. So we're going to say 2 times n times 1 minus n over 1,000 is equal to 0. And just like anytime you're solving an equation equal to 0, you set each factor equal to 0. So you're either going to set n equal to 0 and get n equal to 0, or you're going to set 1 minus n over 1,000 equal to 0, and you're going to get n equal to 1,000. Right, because 1,000 over 1,000 is 1, and 1 minus 1 is 0. And typically when you're finding the equilibrium, we call them, instead of calling them n, we call them n hat. So if it's an equilibrium value, you call it n hat or y hat or whatever your function name is, hat. So now that's great. N equals 0 and n equals 1,000. Those are equilibria. But the other question we want to answer is whether or not those population sizes are stable or unstable. So stability meaning if you're close to them, you'll kind of get directed back towards them. Whereas an unstable equilibrium means if you move away from it just a little bit, you're going to get pushed further away from it. Oh, sorry. That's the way I always think about it. Is stable, you're going to kind of always go back towards it, whereas unstable, you're going to move away from it if you're not right there. So let's take a look. And so there's actually 2 ways of doing this. I prefer the graphical method, but we'll definitely talk about both ways of doing this. Probably. Yeah, we have enough time. So the way to do this is to use a phase plot to help us classify stability, classify stability of each equilibria. So here's what we're going to do. We're going to take our differential equation, dn dt equal to 2 times n times 1 minus n over 1,000. And we're essentially just going to think of it as like we're graphing essentially, although we don't usually change the names, we're just going to think that we're graphing y equal to 2 times x times 1 minus x over 1,000. That's what we're going to graph. So your ends are going to go on the horizontal axis and your derivative is going to go on the vertical axis. When people do this, they often say that we're going to graph g of capital N equal to 2n times 1 minus n over 1,000. That's how it usually gets labeled. But it's really just convenient to think of it like this. We can graph that. It's a function. It's going to be a parabola, right? If you multiply it out, you've got y equal to 2x times 1 minus 2x times x over 1,000 is 2x squared over 1,000 or x squared over 500. Definitely a downward opening parabola. And we even know the x-intercepts. The x-intercepts are 0 and 1,000, are equilibria. So when you're graphing these phase plots, your equilibria value should always be horizontal intercepts on your graph. So let's graph it. So on my horizontal axis, we have the function n, or n of t if you like. On the vertical axis, we have g of n, which is just your dn dt. But the graphing is not that bad. We know we have intercepts that are 0 and 1,000. And we know it's a downward opening parabola, so it's going to look vaguely like this. These graphs should be as bad as possible, meaning you don't want to spend any time making them look good other than making sure you're on the correct side of the x-axis and you're crossing at the x-intercepts. But like that's all you need to worry about, really. I could have made this look much worse and still been fine. Okay, so this is going to tell us everything we need to know about the stability. So here's what I know. I know that between, so in here, for values of n between 0 and 1,000, I know that the function value is positive or negative. Obviously positive, right? If I'm in here, my outputs are all above the horizontal axis, so they're positive values. Okay, but those values are talking about the derivative values. So what you're saying is in this region, the derivative is positive. Okay, if your derivative is positive, is your function decreasing or increasing? So great. So that means the function n, if n starts here, it's going to get bigger and bigger and bigger because we're in the region where n is increasing, where its derivative is positive. Similarly, over here, where n is larger than 1,000, we can see that the derivative is negative, which means n should be decreasing. So anywhere you start over here, you're going to end up getting smaller and smaller and smaller and smaller and smaller. And then, even though it kind of doesn't really make a whole lot of sense to talk about it over here, we can still draw it over here. Same way, the similar idea here, n would be decreasing, but it doesn't really make sense to have a negative number of squirrels. So, okay. So what does this mean for us? Well, it means that 1,000, I should say n hat equal to 1,000 is stable. Or I should say is a stable equilibrium. For exactly the reasons we already said. If you move a little bit away from it, you're getting pushed back towards it. Right? If you start at like a value of 1,100 squirrels, your population is going to decrease until you reach 1,000. If you start at a population of 800 squirrels, your population is going to increase until you get to 1,000. So if you're on either side of 1,000, you're getting pushed back towards 1,000. On the other hand, n hat equal to 0 is an unstable equilibrium. 0 squirrels is an unstable amount because if you have even a few squirrels, they're going to start making not less squirrels towards 0, they're going to start making more squirrels towards 1,000. So even if you start like way over here at like 5 squirrels, you're going to start moving that way towards 1,000 squirrels. Now it might take some time, but that's all we're worried about here. We're just worried about where we end up with eventually. So in general, if the arrows point towards your point, your equilibrium, it's stable. If your arrows point away from your state point, it's an unstable equilibrium. That's the whole kind of deal completely. Yeah, there's one other kind of weird situation, but we'll just questions so far. Yeah, that's kind of it. Yeah. Yeah, it is, but I think I feel like it's easier to graph it, in my opinion. I'll show you another example and kind of talk about it. But like here, right, we like looking at this equation, it should be relatively straightforward to see that it's certainly a second degree polynomial. If you multiply it out, you're going to get n times n, it's n squared, and you have a negative leading coefficient if you multiply it out, so it's going to be a downward opening parabola. But also you can test the point. In fact, sometimes that's what I do. Let's say one more thing about this. So I'll point out you don't need to do this next part, but it's kind of interesting to see what this means like for your population as a function of time. So we're going to use the phase plot. Oh yeah, there is one more question I want to ask here because it's sneaky. So use the phase plot to sketch solution curves. Note the plural there, solution curves. For different initial population sizes. Initial population sizes. Let's say we have initial population sizes. We'll say 200, 700, and 1200. So here's the idea. Now we're trying to make like the regular graph. So our horizontal axis is time, and our vertical axis is the population size. So if we start with a population of, say, 200, based on the thing we just said, as time goes on, the population should get closer and closer to what value? 1,000, right? Because we're starting right here and we're moving that way. So what that means in this graphing situation is that n equal to 1,000 is our horizontal asymptote. And so if we start here, it's going to look vaguely like this. It's going to increase and then it's going to kind of level off, getting closer and closer to 1,000. And that's kind of true for any choice we've made here. If we started at n not equal to 700, same sort of deal. If we started at 700, we're still going to get closer and closer to 1,000 eventually. Even if we start with more than 1,000, if we start at 1,200, we're going to decrease until we get asymptotically close to 1,000. The only way we wouldn't get closer to 1,000 if we somehow started with a negative number of squirrels, which again seems kind of weird, but there's other situations where it makes sense to have an initial population that starts off as negative. So if we had like a negative 100 initial population, we wouldn't get closer to 0 because 0 was unstable. We'd move further away from it. So we'd actually decrease like that, which again, based on our previous graph, makes sense. If you start over here, you're going to get more and more negative. You're not going to get closer to 0. So here's a question that I feel like is going to be too obvious based on what we've just done, but I still think it's worth mentioning because I think people like to ask this question. So here's a question you could be asked, especially if you don't get asked this. Suppose that n at time 0 is equal to 300 squirrels. Find the limit as t goes to infinity of n of t. Now, based on what we've just done, it should be really, I think, straightforward to say, oh yeah, well, that limit's going to be, of course, 1,000. Because if you start at 300, you're going to do the same thing these other things do, you're just getting closer. Or you can look at the previous picture and say to yourself, okay, well, if I look at started at 300, I know we're just going to get closer and closer and closer to 1,000 as time goes on. We'll revisit this idea in a minute. So felt like kind of not the best place to ask that, but still good. So I would not be surprised if you saw a question like this at some point where you were given the differential equation, you did the phase plot, and then you're told some starting place and asked to find this limit. They're just asking you if you start on some place along your horizontal axis to what value are you getting pushed towards. So I do think when you draw the phase plots, you really should draw the little arrows on the horizontal axis. It makes everything easier to figure out what's going on. Okay, let's look at another example. Yeah, we got time. So let's say we have a slightly different situation, but similar. Let's say now our dNdt, our rate of change of our population size, is equal to 3 times n times 1 minus n over 500 times n minus 60. Same questions. First question, find the equilibrium. In fact, I want you all to write them down right now. Find all 3 equilibria. They should be pretty easy to see what they are. Two of them are really easy, 0 and 60. The third one, a little more work to see that it's 500. But those are your 3 equilibria. And I'm just seeing those by setting each of the factors equal to 0. This one equal to 0, obvious. This one equal to 0, obvious. This one equal to 0, slightly more work, but not too bad. All right, part B, let's make a phase plot and classify. So use a phase plot to classify each equilibria. So let's see here. Phase plot. So we have our horizontal axis is n, and our vertical axis is g of n equal to dn dt. Again, we're really just thinking of graphing y as a function of x. We're just not using y and x. All right, so I'm going to put all my equilibria on my x-axis. So 0, 60, 500. They don't really have to be spaced out equally at all. You just have to make sure that they are in the right order. Now, here's where I might take your advice and plug in a point to see if things are positive or negative, at least for one of them. So like if I plug in something between 0 and 60, like 1, 3 times 1 is positive, 1 minus 1 over 500 is positive, and 1 minus 60 is negative. So a positive times a positive times a negative is going to be negative overall. So I know between 0 and 60, my graph is going to be below the horizontal axis. So I'm going to have negative values down here. And then here's what I'm going to do. Instead of continuing to plug in values, I'm going to utilize the fact that each of these factors is raised to an odd power. And when the 0 came from a factor that's raised to an odd power, the sign of your expression changes when you go from one side of a 0 to the other side of a 0. So over here, between 60 and 500, our whole value should be positive. We can check if you want to. If you plug in, say, like 100, 3 times 100 is positive. 1 minus 100 over 500 is still 1 minus a number that's smaller than 1, so it's still positive. And 100 minus 60 is also positive. So it's a positive times a positive times a positive. The whole thing's positive. So we're positive in this region. And then when we come back down towards 500, we're going to cross again. Oops, I missed it. Oh, well. And then also to the left over here, this graph should continue up this way. You can check if you want to, but since all of my factors are to odd powers, we're going to cross the horizontal axis every time we hit one of those zeros of that function. Okay, now we're going to draw the little arrows. So when the graph is above the axis, the arrows point to the right. When the graph is below the horizontal axis, the arrows point to the left. So over here, my arrow should be pointing to the right because our function is increasing. Over here to the left, over here to the right, over here to the left. So which of these is my only unstable equilibrium? 60. So n hat equal to 60 is unstable. The other two are stable. So n hat equal to 0 which might not make sense as far as like a population growth sort of situation, but okay, fine. Sometimes the examples fall apart if you make them too weird. So n hat equal to 0 and n hat equal to 500 are both stable. So now let me ask you all a question. Given n at time 0, or does it have to be at time 0? Let's say n at time 10 minutes later, or 10 years later, or 10 whatever units of time we're talking about later. Let's say n of 10 is equal to 123. Find the limit as t goes to infinity of n of t. This is really just a look at the graph and write down the right number kind of question. All right, so we're starting somewhere here, which means we're getting pushed towards 500. So that limit better be 500. That's it. Kind of not exciting. But people like to ask this question, so that's why I felt like I should mention it. Let's see, what else do I want to say here? Yeah. Okay, so you don't have to do this the graphical way. I like the graphical way. I think it's easy and relatively straightforward, but sometimes the graphing part can be a little challenging. So one thing I'll point out is if you look at both of our examples here, when the equilibrium was stable, the function we graphed had a negative derivative, right? The slope of the tangent line right there is for sure negative at that stable equilibrium. Same deal over here. For both of these, oh God, maybe. For both of these stable ones, the derivative there is negative, the derivative there is negative. And for the unstable ones, the derivative of our function we've graphed is positive. Same deal here, right? Unstable, derivative is positive. So another way to classify stability of equilibria without using graphs is to find your equilibria and then find the derivative of the function that we've graphed, meaning we actually have to find the derivative, and then plug in your equilibria and see. So let's actually do that for the one we just did. So here's the non-graphical method. I feel like there's a better name for it. It might be called like the analytical method. I don't know. Non-graphical method for classifying equilibria. Equilibria stability. Fine, let's look at the same example we just did so we can really kind of see it. So for dn dt equal to 3 times n times 1 minus n over 500 times n minus 60, we found that our equilibrium values were 0, 60, and 500. And this is where it actually is useful to call this the function g of n. G is the typical choice. I couldn't tell you why. So now what we have to do is we have to take the derivative of this function, which is going to be kind of a pain. So before we take the derivative, it might make sense to multiply it out. Yeah, it kind of does. It's not my favorite, but oh well. So we're going to say that g of n, we're going to distribute the 3n here. So we're going to get 3n times 1 minus 3n times n over 500 is 3n squared over 500. Still times n minus 60. Ugh, ugh. See why I like the graphing method? And then multiplying this out, you're going to get, let's see, 3n times n is 3n squared. 3n times negative 60 is minus 180n. Minus 3n squared times n is minus 3n cubed over 500. And then minus 3n squared times negative 60 is plus 180n squared over 500. Okay, that's kind of gross, but not too terrible to take a derivative of. G prime of n is going to equal 6n minus 180 minus the derivative of n cubed is 3n squared, so it's going to be 9n squared over 500. And then the derivative here is going to be 360 times n over 500, which I could probably reduce that fraction to like 36 over 50 or 18 over 25. That's 18 over 25n. But I'm not going to worry too much about it. because all I really want to do is plug in these values and see if it's positive or negative. So let's look at 0. Now, based on our work before, we are expecting plugging in 0 to give us a stable equilibrium, meaning the derivative should be negative, right? Look back at our graph. 0 is stable, and it had a negative derivative there. All right, let's see. So g of 0 is going to be 0 minus 180 minus 0 plus 0. Yep, looking good. So 0 is stable. Let's look at the other ones. It's gonna be a little bit grosser here. Oh, yes, ugh. Don't love it at all. If I plug in 60, I get 6 times 60 minus 180 minus 9 times 60 squared over 500. Ugh. Plus 18 times 60 over 25. It's probably positive. I don't want to do that math. I'm just going to say it's positive because it is. So it's unstable. So this example, not great for doing it the non-graphical method, right? It really is like super pain. And then G of 500, again, I'm not going to do the work. I'm just going to tell you it's for sure going to be negative, which means n hat equal to 500 is stable. Let's look at one more example that's a little less terrible to do this way. So let me look here real quick. So I think the graphical method is really great, especially if your functions essentially, or your differential equation is equal to a polynomial, especially if it's kind of already factored for you. That's a real decent opportunity to use the graphical method. But if you have something that's not a polynomial, it could be less easy to graph. For example, let's say we want to find and classify the equilibria of this differential equation of, what do I got here? dy dt equal to 4y times parentheses 3e to the negative y minus 2. Okay. I don't know how to graph that. I mean, not without Desmos, but we could graph it on Desmos, but let's not. Let's go ahead and just start by finding the equilibria. So first, the equilibria. Well, I bet you can all see one of them real easily. One of them is going to be y hat equal to 0. The other one is going to be setting this part equal to 0. So we're going to set 3e to the negative y minus 2 equal to 0. Add 2. So 3e to the negative y equals 2. E to the negative y equals 2/3. Negative y equals the natural log of 2/3. So y hat is equal to negative natural log of 2/3. Which you might rewrite if you wanted to as the positive natural log of 3/2. Right? If you bring that negative one up as the exponent, it changes, it gives you the reciprocal of 2/3. Either way is fine though. Okay, let's not use the graphical method here. So instead, we're going to use the other method. So we're going to find g prime of y for our function g of y equal to 4y times 3e to the negative y minus 2. Okay, so we're going to use the product rule here. So g prime of y is going to equal 4 times 1 times the other stuff left alone plus 4y times the derivative of the other stuff. The derivative of 3e to the negative y is 3e to the negative y times negative 1. And the derivative of negative 2 is 0. And again, I don't think it's worthwhile to simplify this because we're just going to try plugging in some values and see what happens. So first we're going to plug in 0. So g prime of 0 is equal to, let's see here, 4 times 3e to the 0 minus 2. 3e to the 0 is just 3 times 1, so you have 3 minus 2, plus 4 times 0 times, I don't care what any of this is over here, it's not going to matter. So don't think about it. So let's see, I'm going to get 4 times 1, which is 4, which is positive, which means that y hat equal to 0 is unstable. I'll refer you back to our graphs. Just to really drive the point home, right? This one here was unstable, and the derivative there is certainly positive. Questions? I see questions. Yes. So I didn't actually do the work last time because I was like, it's kind of ugly. But if you actually calculated this, G of 60 here, 60 times 6 and 60 is 360 minus 180, that's 180. And then 9 times 60 squared over 500 is 9 times 3600. Okay, sure. That's not even close to 180. So this is definitely positive. This is 180. This is not even in the realm of 180. That's positive. So for sure, this whole thing's positive. But I didn't even want you to look at that really. What I wanted you to look at was the fact that on the graph at 60, is the function increasing or decreasing? So it clearly has a positive derivative because it's an increasing function there. So if the function's increasing at your equilibrium, we know that equilibrium is unstable. On the other hand, well, let's see. Let's see what happens when we plug in the other one. They could both be unstable. It could happen. So let's say we plug in y hat equal to negative natural log of 2/3. No, that's fine. So we do that, we're going to have g prime of negative natural log of 2/3 equal to, now let's be smart about this. I'm going to have 4 times 3e to the negative natural log of 2/3 is just natural log of 2/3. Minus 2. Interesting. And then we'll have plus 4 times negative natural log of 2/3 times 3e to the natural log of 2/3 times negative 1. Ooh, it's getting a little tight over here. All right. E to the natural log of 2/3 is just 2/3. 3 times 2/3 is 2. 3 times 2/3 is 2. Let me say that one more time. 3 times 2/3 is 2. So we have 2 minus 2. This is all 0 right here. Okay. So this part over here, all right, it's going to be real interesting. We have 4 times negative natural log of 2/3 times 3 times negative 1 is negative 3. And e to the natural log of 2/3 is also 2/3. So you have negative 2. All right. This is tricky. If you looked at this without doing enough analysis, if you can see things here, you might look at those 2 negative signs and think this whole thing was positive. And it's not. Because natural log of 2/3 is a negative number. Because it's natural log of a number that's less than 1. So if you wanted to, you could rewrite this part as positive natural log of 3/2, which is a positive number. So it's a positive times a positive times a negative, which is negative. Which means this equilibrium is stable. So again, be careful if you've got logs in your answer. Just remember the graph of the natural log of x, right? If you graph y equal to the natural log of x, it is positive if your input is larger than 1. It is negative if your input is between 0 and 1. And 2/3 is definitely between 0 and 1, so it gives you a negative output. So negative is positive. Okay. A little bit tricky, but worthwhile. And that's probably a good place to stop. Yeah, it is. All right. See you all on Monday. Have a lovely Halloween. Make good choices. See you all on Monday.
Question.
Mhm.
So for the next, so if you're getting natural log 2/3, is